And we're live.
Hello, good evening or good morning, depending on where you are. Welcome to the March Research Showcase. My name is Miriam. I'm a research scientist at the Wikimedia Foundation research team. And today at the Research Showcase, we have two amazing presentations from Thomas and Besnik. And in these Hangouts, we have a bunch of other members of the research team, Jonathan, Isaac, Leila, and Diego. So first up today, what's going to happen is we're going to have two presentations. And after each presentation, we are going to have a few minutes for questions. And then maybe at the end of, we can have a discussion for if we have some other questions for the speakers. So first up today is Thomas, a PhD student from Télécom ParisTech, who's going to present his recent work about learning how to correct Wikidata. This is work which is going to present it at the web conference in May. And so I think with that, Thomas, the stage is yours.
Thank you. Let me set up my slides. Here we go. So I'm going to present our paper that we called Learning How to Correct a Knowledge Base from the Edit History. So actually, we did most of the experiments of this paper on Wikidata. So I'm going to focus the presentation mostly on Wikidata, but on the actual paper, we present formalisms that could apply to most of the knowledge bases. So if you are interested in something more general than Wikidata, please just have a look at it. But this presentation, so this is joint work with Camille and Fabian. I'm just going to focus more on Wikidata and how we could fix the constraint violations on Wikidata. Sorry, so as you know, Wikidata is, let's say, kind of messy. You have a lot of violations of Wikidata constraints. So Wikidata constraints are mostly saying that, for example, you should have only one birth date or a set of possible supposed values for the sex or gender property should be most male, female, transgender male, transgender female, and so on. But there are still a lot of violations for this constraint. So as you say, in this statistics from July 2018, we still have constraint type with more than 3 million violations. So in this work, we wanted to try to help to see if we could find good automated ways to help reducing this kind of violations. So if you have already worked on fixing these violations, there are often some patterns that could emerge. So for example, here we can take a look at an item. You see that you have a violation for the sex and gender relation. You have the woman value, and you see that there is a problem because it's not supposed to be one of the possible value for the sex and gender property, and you see that probably if the value is woman, then it should be replaced by female, and so you could write it as a rule saying that if there is a violation for the one-off constraints for the sex and gender property where the value is woman, you should replace the value woman by the value female. And if we take another example, here we have an entity about a person. He has a place of birth, and then you see there is a violation on the value type constraint for place of birth, saying that actually the value should have a type that is a geographical object or fictional location and so on. And then you see that the value has actually is in a country. So then you could probably infer that it makes sense to add the type geographical object to the value. And so you could also write it as a rule saying that if there is a violation for a given, for this place of birth relation, for this constraint, and the object of this relation has the country property, then you should add the type GeoObject to this value. And so in this work, we want to mine such rules to suggest people that curate the knowledge base and the people that edit Wikidata simple edits to solve these violations. And so why are we focusing on rules and not other things like, for example, more statistical machine learning approach? Is because rules are explainable. The idea is that if you suggest an edit to do to the user, you could say you have applied this rule, and so the user could know what the algorithm did actually to suggest this this edit. And the other nice thing is that rules works well with new entities. So, for example, if you add a new entity in Wikidata, the rules could easily apply on it. You don't rely on things like embeddings. You may want to learn on all entities and so on. And so for retrieving, for any rules, we need data. And what is very nice with knowledge base like Wikidata is that you have a full edit history of all what Wikidata contributors have done on Wikidata. And so you can have a look at it and see, for example, if before a revision you have a violation. So here you have a value type violation, and then there have been an edit, and then the violation disappeared. Then probably the revision, then you know that the revision fixed this violation. And so hopefully the revision is the proper way to solve this violation. And so what we did is that we extracted that from the Wikidata history to be more specific. What other finding is that actually when you have a look at constraints, there is two atomic ways to solve a violation of Wikidata constraints. It's actually to remove a fact or to add a fact. For example, you see that here, the two for this value type constraints for place of birth, the two possible ways to solve the violation is actually remove the place of birth fact or add a type, and it generalizes on all constraint types in Wikidata. And so what we actually do to build the dataset is have a look at for each constraint type, you have a look at the edits that does this thing. So for example, here, say remove a place of birth, of add the geographical object type, and obviously there are subclasses, and also for fictional location and so on. And then we check if these edits were actually fixing constraint violation. And if it is the case, we just add it to the dataset. So for that, what we did is that we actually wrote SPARQL queries, not against official Wikidata query service, but we built our history query service that basically loads all the. So what we have in it is the Wikidata mean value relationships, so the WDT relations you could have in Wikidata query, but we have it for all Wikidata revisions with also revision metadata. If you want, it's enabled on Wikimedia cloud services. So I'm going to leave the link at the end of this presentation if you want to use it for doing research on Wikidata. So it has been very helpful for us. And so with that, we have been able to extract more than 75 million of past corrections on Wikidata. And so we created a big data set. It's also available online. So the link is going also to be at the end of the presentation and is also in the paper that basically states that at this given revision, this violation. So here, for example, in the first line of my example, the value type constraint for place of birth for the person called Matsubacho with a value is for a given specific value led actually to this edit. And so we have it for all our samples, and from that we were able to actually learn rules. So how do we do it? So as I just said, our goal is to generalize from this data set. So here, for example, we have three ways to solve, three examples of solving or example constraints, or the value type for place of variation constraint type for place of birth. And we want to basically the idea is to generalize these examples to get a rule. So for that, first we need to do it in two steps. The first one is to generate rules that may be interesting. So first, So for that, we take each rule in our each basically instantiated rule in our dataset that corresponds to also past correction. So you see here, it's not a rule, it's just one, let's say, correction of a past violation. And then we generalize it by basically replacing or not. So we basically each constant by a variable. Here we replaced most of the constant by a variable, but you could also, obviously we also generate rules where less, where more constants are still there. So it creates a lot of possible rules, and then we also want to expand it to take care of the context, because, for example, for the example we have seen, often the context is useful. For example, if the value of place of birth in the country, then it's likely that it is a geographical object. But if the value of place of birth has a birth date, then it's probably a mistake and we should remove the place of birth statement. So having the context is interesting, so we wanted to keep it in the rules. And then, so we have generated this rule, but we want to find which are the good ones we want to keep. So for that, to explain it, I need to introduce some vocabulary. So here we have a rule, and we define what is a rule body and a rule head. So the rule body is basically the if part of the rule. So here it's if there is a violation for the value type constraint on place of birth for variable s and variable p, and then in the Wikidata graph you have that p p as a statement with a country relation. So this is a rule body, and then you have the rule head. That's what we are going to do. Is so we are going to add this this statement or remove this statement and so on. And so basically, the rule body and the rule head could be seen as queries on our past correction dataset plus the Wikidata graph at the revision where the violation solving happened. And so we could define the support of the rule body and the support of the rule head as a number of times the corresponding query matches. So for example, it's if you have a look at the support of the rule body here in this example, it's a number of times we have add in our data set a violation for place the value type constant of place of birth, and that the place has a country statement. And with that, we could define how we run the rule. So our intuition for that is basically saying that a rule is good if it predicts the correct changes. So the idea is that if the rule predicts the good corrections, then it's fine, and it's a good rule. If it does not predict the good corrections, it's a bad one. And so we define the confidence of a rule, saying that it's basically the number of times the rule applies. The rule could apply and applies and gives the correct output, or the correct edit, and divided by the number of times the rule applies in the dataset. So if I take an example, was the rules are saying that we should replace for the if you have a violation of the one-off constraint for the gender relation with the value woman, you should replace the value woman with the value female. And we have a dataset of 3 examples of corrections for these constraints, 2 that replace woman by female and 1 replace woman by male. We say that so the body of our rule R here is just saying that the violation matches 3 times in this example dataset, but the rule head, so the edits we should do, is only correct twice, and so the confidence of our rule here is only 2/3. And so we thought we could, with these 2 pieces, we could do our rule mining algorithm. So we just first take our data set of past correction, we generalize it by introducing variables, and then we just remove out all of the basic rules that have a too low body support. So the idea is that we don't want to keep the rules that only applying in the dataset in 1 or 2 or 3 cases, because they are not general enough, and so not, let's say, not interesting enough to keep to predict corrections for new violations. And then what we do iteratively, we add context reports, and then we only keep the context reports if they keep a good enough body support. to keep having general rules, and if they also, and we want also to keep it only if they increase the rule confidence. So they had a value, because we do not want to have a context that does not improve the rules and does not give new information that helps to find the good correction. And then when we have iterated on this algorithm, we just keep the rules only that have a good enough confidence. So in our experiment afterward, we just keep, for example, keep a threshold on 0.5 on it, but it's we could pick some other thresholds, and it also gives interesting results. So we applied it on our 80% of the past correction we made, and we found nearly 200,000 rules. If I pick some example of top rules, so we run for each constraint type, so one R, single value, value type, and so on. We sorted the rules by first decreasing confidence, and then if the confidence was the same, by decreasing support. And the top rule, for example, the top rule for single value type constraint was about the gender relation, and was stating that if the value for the gender relation is if the gender relation have multiple values, and one is monogamism, and is also the subject of the relation is also in a sports team, then you should remove monogamism. So it's quite funny that we have this rule top. It's probably because some bots or automated system introduce a lot of these values for sports member, and then fixed the problem. And so here we actually learn how to learn this fix. If I take another example, it's for the one-off constraint here, saying that targeting the manner of death relation that has only a very specific set of values, and saying that the value of this relation in traffic accident, then it should be moved from the manner of death relation to the cause of death relation. So this rule also is quite nice, because you see how you not only removing the bad value, it's moving it to something else, and so actually improving well the knowledge base. So with that, we did the first experiment of our system. So what we did is we applied the rule we mined of the correction we did not use to train the rules, and then we computed two metrics: the precision of the recall. So the recall metric is used to know how well we were able to actually predict some correction. So we just compute the number of past it just computes the ratio of the number of past corrections for which we are able to find a correction good or not, and then the precision targets only the corrections the possible correction we found, and gives us the ratio of correct one. And then we compare the approach to two, let's say, simple baselines. The first one is removing the violation main statement, so basically the statements that has the violation warning in Wikidata. And the second one, so it doesn't work for all constraints types, but what it does, it had a missing triples that could fix the violation. So for example, for the value, the type constraints, it has a new type to the subject of the statement. And so our results, so here we do not put in precision or recall, but to keep a simple unigraph, we keep the F1, that is basically a combination of precision and recall. So you have here our system we call Chorist in yellow, and we compare it to two baseline, delete in brown and add in blue. And you could see that except for single value and missing values constraints, we our approach significantly outperform our baseline. So it's stating that actually mining rules instead of suggesting that the dumb things works quite well. Two interesting points. So for inverse symmetric, actually, the at baseline is very good. It's probably mostly because for this constraint is saying the good correction is nearly all cases just adding the reverse triple. So for example, if the roads A crosses the roads B, then the roads B crosses the roads A, and it works very well. And for single value and distinct values, we are have actually better precision, but a very small recall. And it's mostly because these constraints are applied in nearly all cases for external identifiers, and we do not have any description in Wikidata of the external identifiers themselves. So we are not able to mine rules that know something about the external identifiers, and so we have no rules for most of the relations that have these constraints, and so very small recall. And so it's still an open problem to know how to suggest a good correction for violations for these external identifiers. And so we did also another experiment that is also a way to give back the result of our work to the Wikidata community. We created a Wikidata game that suggests corrections for the constraint violations. So we run the tool. So in the statistics I'm going to give, it was for the first 3 months of the life of the Wikidata game. We had nearly 50 participants, and we loaded into the tool database nearly 50,000 suggested corrections. And so we have very mixed results with respect of constraint types. I'm going to describe it, have them here. So first, for the inverse and symmetric constraint type, we had 22,000 actions, so approve or reject the suggested correction, and with a very high approval rate of 92%. It's mostly because there were still some, let's say, easy fix to do that applied a lot of items. It was mostly actually words in the Japanese network in our sample. So some user actually approved a lot of the statement, so it gave us a very good ratio, but it's probably stuff that could have been done by bots. And then for value request statement conflict with relations, so we had also a significant number of actions for each one, more than 1,000, and very good approval rate. So we also found good rules and applied in a lot of cases, and were not already done by Wikidata users and bots. And then for the other ones, we have often much lower number of actions and much lower approval rate. And if we played with it, my impressions also have nothing to support it. Is that most of a lot of the cases there were in a lot of cases we had bad rules that gave us suggestions were the bad things, but we also had a huge number of, let's say, hard violations, whereas that are often edge cases and so on, and so it's not for them it were not very easy to just guess what were the good way to fix the violation. So it's actually things quite challenging and interesting. So we have in the violation that remains, we have a lot of biases, let's say, with respect of what have been done by bots or not already, and we still have a lot of hard stuff that remains, and so for which we need to find good ways to suggest good corrections. So to conclude, in our work, we first provided, I believe, what is an interesting data set of past corrections on Wikidata. So it's probably quite interesting learning test to know how to find a good correction for content violations. And then we provided a first approach for this problem based on mining. This approach has been significantly better than baselines in a lot of cases, and has also the advantage of being understandable because we mine a rule and then we could state to the user suggesting this correction because we apply this rule, and so because there is this specific case that happens, and so we have some let's say an explainable AI system. And then let's say second point on the conclusion that with bots on Wikidata, easy stuffs are mostly already done, and so there is still mostly, let's say, hard violations that remains and may need more powerful tools like full mining to be solved. And so it leaves us some quite interesting problem. I think the main interesting, a good example of them are the problem like there are 2 birth dates or a birth date is missing. Because for this, we could not only work with Wikidata because we didn't have the way from Wikidata only to know which of the two birth date, for example, is good. And often when you have to deal with these violations, you need to check the sources, so Wikipedia and so on, saying if the violation is okay and there is two attested birth dates, and so we should keep them both on Wikidata, or we should keep one because the second one is not attested at all, and so on. So it needs external information, and so it would be interesting to have systems that are able to use this external, it's not Wikidata, not knowledge-based knowledge, to solve this problem. So if you are interested to work on it, I will be very interested in collaborating. And so the second one is, I think that for the future is that we had a look here at how the fixing constant violations, but similar approaches could maybe be used for other things. So for example, to suggest users edits. So for example, let's say I am doing a specific correction in Wikidata in all instances of this class and already done it for the 21st, then I could have a system that suggests me, hey, I have seen you have done exactly the same edits on these 20 items. You have 30 other similar items. Do you want to apply the same edit? And so it would help, it would probably allow some users to earn a lot of time, but mostly automating a part of their work without having, let's say, to write bots or scripts and so on. And the other thing is maybe that we combine rules to solve constraint violation, but actually what the rules give us is what is a likely edit to do. And so we could, I'm not sure if it's a good idea, but it could give us an idea of if for some edits, if the edit is likely or not. And so if the edit is not likely, then may have a higher chance to be vandalism. And so it may be more interesting for batching contributor to have a look at these edits first. So thank you for listening my presentation. There was the links for different things I discussed here. So the paper, the Wikidata game, and so on. The slides are on the showcase wiki page if you want to read them or use the links. So thank you.
Okay, thank you very much, Thomas, for this amazing presentation. So it's time for a Q&A session. We have a few minutes for that. I want to hear from the IRC host, who I think is Isaac or Diego. If we have some questions from IRC or YouTube.
No questions from YouTube.
Nothing from IRC now.
Okay. Do we have any questions from the room here, from the Hangouts? Leila.
Thank you. Can you hear me fine?
Yes.
Great. Thomas, thanks a lot for the presentation. So my question for you is, for outside of the Wikimedia world, if we want to apply the method that you developed for external knowledge bases, how would the edit component work? Is the idea, the edit history component, is the idea that you will have to have an intermediate stage where you provide basically these labels, and then based on those labels, basically the rest of the pipeline can be developed? If you can speak to that, that would be great.
Yes, indeed. So, so we need some data set to learn, so some labels to learn how to learn the edits. So you basically need to have some kind of maybe change system when you have a before state with a violation and after state without it. And then instead of the change, we could have a look at what have been the triple additions and deletions that actually fit, that were local enough to fix the violation. So if you have a look at one of my previous slides, yes, exactly this one, you see that even if let's say the change had multiple thousand triples added and removed, we could have a look there what have been the actual triples that solve the violation. Because from the constraints, we know that only some triples could actually solve the violation. To have specific triple pattern from them. And so as soon as you have it, you could apply it. So let's say I have a knowledge base derived from Wikipedia, and so I run my conversion pipeline, let's say every month. And I have a constraint system, and for the diff between 2 months pipeline executions, I could have a look at what have been the changes, and so also get from it what have been the good, the interesting addition or deletions that solved the violations. Does it answer your question?
Yes, thank you.
Thank you, Leila and Thomas. We do have 2 questions from the YouTube stream. So one is about, can you share the presentation? I think it's on Google Slides, so it's a shareable link. I don't know, you can say if you can share the presentation.
Actually, the PDF is on Commons, and the link is on the Wikimedia Research Showcase wiki page.
Okay, perfect. And the other question is about related work and essentially existing research around this this problem of correcting knowledge bases. If you can share a bit of knowledge about existing work in this space. Thank you.
So actually, my impression is that most of the work on improving knowledge bases have done a completely different approach. So instead, here we are basically having looked at what the changes the user have done to the knowledge base. But let's say before Wikidata, knowledge bases were not having, let's say, except maybe Freebase, were not having, let's say, big edit history and a lot of users collaborating and the users fixing problems and so on. So it was mostly, let's say, like DBpedia or Yago that were completely extracted from Wikipedia, or Freebase that were probably mostly improved by, increased by automated systems, and so on. And so we're not focused on it, but there mostly been work, let's say, on using the constraints themselves. So, for example, there have been works that if you have some constraints rules that's, for example, expressed in description logic, then you could find what is the smallest subset of facts to remove to curate a knowledge base. So we have in our paper, we have a section that's related works that talks about these things. You may want to have a look at it. Sorry, I don't have the name of the papers here in my head, so I'm not able to give them to you. But you definitely should have a look at the related work section.
Okay, these were the 2 questions from YouTube. I think we can keep other questions, if any, for the end of the other presentation, and maybe we can pass to the second presentation of today from Besnik. If Thomas, if you can stop sharing your screen, I think Besnik can share his. Yes. Okay. Hello, Besnik. So the next presentation is from Besnik, who's a postdoc at L3S Hanover and a formal collaborator of the research team. He's going to present some work about Wikipedia tables, and this is another paper which is going to be presented at the web conference in San Francisco. Besnik, I'm not sure we can see your screen.
Can you? Yeah, that was my question. Because I kind of put
yes,
to full screen.
Maybe
I just open the PDF. It's probably easier.
Whatever works for you. So the presentation doesn't work. If I think this is, if you can zoom a bit, maybe this can work. No problem. Okay, so the floor is yours, Besnik.
Thank you. Are the slides visible now?
Yes.
Okay.
If you can maybe zoom a bit on the central slide, I think it would be easier to see the text. But
I did. I put it in full screen now. So.
Besnik, sorry, we don't
Yeah.
see that full screen. So I'm not sure. Maybe you have not shared your entire screen, and that can sometimes happen if you just share the window. It doesn't show the. Full
Yeah, I see. Okay, let me redo it again. Is it better now?
Great, thank you.
Yes.
Okay. Yeah, sorry for this. So yeah, thank you, Miriam. Thanks for the invitation. Yeah, so I'm a postdoc at the LTRS Research Center here in the University of Hanover. I'm going to talk about some recent work, which we kind of coined with the term TableNet. So what we try to do here is basically come up with an approach which for given some pair of tables, let's say in this case Wikipedia tables, you can determine the relations between such tables, and the relations have to be fine-grained. So I will kind of mention later like what type of relations we are interested in, what relations are possible in our setting, and the work, the paper you can find in the GitHub page. I published there the data, and some of the code is going to be published soon before the conference venue, which is sometime in May. So, so the first question, like if you're considering tables, is like, why actually do we bother about tables, right? So, what is so important about them? So, tables in general, they contain factual information, and especially if you consider the Wikipedia tables, they are very rich in such a type of information. For example, here you have the 100 meters running race, right? So this is a Wikipedia page which contains a table about continental records, and this table, for example, contains different categories about men and women. It groups these individuals into the different continents and has information about their time with which they finished this 100 meters race, and so on and so forth, right? So this is quite interesting. And then you have another table in the same article, which is about what are the season's best results in this type of race. And this table is about the category of women, and you see them chronologically ordered from year 1972 until nowadays. So now this information exists a lot in large numbers in Wikipedia, and however, it is there mostly like for let's say of course to kind of show these facts, but they exist sort of in isolation. So so this kind of like links a bit to the previous presentation about knowledge bases, where you have this factual information, and usually they are used in question answering, and you have some question, and then you kind of query the knowledge base, and then you get a factual answer. So, but if you consider more complex questions, there are almost no resource that can answer such questions. For example, here, if you want to answer what is the time difference for the best time in women's 100-meter race in 1974 and 2018, you would not be able to get this answer, let's say, from one single source. But we saw before that we have multiple tables which are scattered in isolated, or the information is isolated in different tables, different articles, and basically you cannot really get easy access to such kind of answers, right? So, so now if I kind of put these tables side by side, we can clearly see that if I pick year 1974 and 2018, so in 2018, we have one person from United States, and basically then the answer would be like the difference is less than a second. So, but this information, obviously you would need to know that these two tables are related in order to kind of like come to the idea of joining them for providing one single answer, right? So this is kind of the why tables are important to kind of use for question answering tools or for any other type of research. In Wikipedia, there are more than 530,000 articles which contain tables, and we've extracted all of these tables, and roughly right now there are more than 3 million extracted tables, and these each table has roughly like on average 10 rows, and if I'm not mistaken, around 6 columns. So if you like just kind of sum up these numbers, you get like more than 32 million rows. And what can happen with this type of information is that if you kind of like convert it into facts, you can get like hundreds of millions of additional triples, which can go into knowledge base like Wikidata or any other knowledge base. However, these facts are much richer than let's say the info boxes, which are used mostly for knowledge base, because the info boxes have like a very strict template, and they have only a specific type of narrow information, whereas in tables you have like really rich information spanning in multiple topics, multiple time points, and so on and so forth. So actually harnessing this information is very important. So in Wikipedia tables, obviously, so what we had to do, so you can find the extractor code in the link below in the slides. What we had to do is we had to account for the different type of tables that exist in Wikipedia. So you have to remember that in Wikipedia, tables are kind of optimized for human readability, right? So they have to kind of make sense when a human reads those tables. But if you go and kind of try to process them automatically, they are like very different representations, and it's not very trivial to kind of infer some structure that you can then basically use later on to extract these rows from the table. For example, here you find that you have 3 columns. However, in the first row, you have the cell, the second cell, which is spanning on all 3 columns. And then you have like column headers, which span multiple rows, as the case here with season. Then you have multiple layers of column headers, like for example here, originally released, then you have first released, last released. So the inferring the table structure is not so trivial, and this is one kind of first challenge that you encounter when you try to extract these tables from Wikipedia. So we did that, and I won't go into details how we did that, but we published them kind of in a JSON format, and with all the different, we have some schema that we infer for these tables, and we distinguish between values which are hyperlinked to some other article, and what we call instance values, and to other primitive values which are just let's say string, numbers, dates, and so on, so they do not link to any Wikipedia article. So this is how you can you will get basically the table data, and you can download already all these 3 million tables, and yeah, so you have this JSON structure which you can then use to do further processing. Okay, so this is kind of like just an intro into the tables problem and tables in Wikipedia. So what are the challenges, and what are some of the opportunities that we can basically use? So as I said, there's no explicit schema which defines this table. So what does a column mean? Like you might have a column called the name, but this name might refer to various different things. For example, name of actors, scientists, race types. It can be anything, right? So the challenges here, like how do you infer such representation for a column? Then, of course, as I said, the representation is meant for human readability. So you might get the content of the table in HTML or wiki markup, but in both cases, this is meant to increase the human readability. And in each of these tables, there are several kind of columns which are seen as more important, without which the information in the other columns does not make any sense. For example, if I remove in the previous example, the athletes' names, so then those numbers about the race time and so on, they are meaningless, right? So now if I want to kind of like align these tables, then I need to take all this information into account. So that's what we propose. So we have this table length approach, and what we want to do is basically automatically extract tables from Wikipedia and efficiently align these tables with high accuracy, which is highly important. But we also want to retain high coverage. So for each table that I consider, let's say, as my source table, I want to have a coverage guarantee that I am able to find all the, or with a high coverage, the related tables and define such relations. One example is, again, dealing with this 100 meters race article. And then here in the leftmost table, you have the continental records, and these are the best records in this race, which basically can go any type of athlete that does this race. And on the right-hand side, you have the more specialized tables, which are all-time top 25 women, men, and under 20, so for the juniors, right? So here we have different type of relations between the tables. So for example, the leftmost table with the rightmost tables, you have this subsumption relation. So basically the leftmost table kind of contains semantically the three other right tables, whereas the right tables, for example, all-time top 25 women and all-time top 25 men, they are kind of equivalent because they are talking about semantically similar information. And so basically I can align them saying that they are equivalent in the sense of they represent semantically similar information. And on the other case, basically there's this subsumption, so that in the leftmost table can contain theoretically all the information coming from all the three other rightmost tables, right? So this is kind of the alignment objective. So to do this, as I said, there are quite some challenges. So the first part is to extract these tables, and how do you kind of infer the schema and generate a schema for these tables. So I'm not going to talk about that because I think there would be no time for that, but you can read the paper, or you can just look up the code how we do that. I'm going to focus more on the for any given Wikipedia article that contains tables. So how can I generate candidate articles who also contain tables such that I can basically find with high coverage and the tables which can have a relation. And once I have this candidate set, I have to decide which of these table pairs from my source article and the candidate articles can be in an alignment, right? And we will see later on what are these type of, so as I said, equivalent and subpart of relations between tables. So for the first step, the candidate pair generation, as I said, we have more than 530,000 Wikipedia articles. So if you want to ensure coverage, then basically comparing everything with everything, this leads to a combinatorial explosion. So it's not doable. What you need to do is you need to come up with efficient ways to kind of generate these candidate pairs such that you reduce the irrelevant pairs, but at the same time you keep high coverage of relevant article pairs. And for that, we propose a set of features which leverage the Wikipedia articles themselves. So the first set of features basically is so because we define that equivalent or subpart of means that the information in these two tables has to be semantically similar. So basically they have to be of the same topic, or instances in those rows should be semantically related. Therefore, the best or the first entry point to kind of check for this consistency is that you look at the article abstracts of you have two articles here, for example, Game of Thrones and The Handmaid's Tale. So you see that both are TV series, and there should be some kind of lexical cues that give away that these two articles are talking about the same kind of type of information, namely TV series, right? So for that, what we did basically was that you compute these representations of the articles. We use talk2vec for that, so it's similar to board2vec, just that kind of captures more contextual information, and then we compare their representation and see that if it's above some threshold, then we say, okay, these two can kind of can generate a candidate, can generate a pair. And similarly, we also use more traditional IR features like TF-IDF. The reason for that was that if you use like word2vec or doc2vec, so what you're not really capturing is the importance of the different terms. And this is what the TF-IDF term scoring captures, so that basically you try to see if the two Wikipedia articles have these discriminatory terms in both of their abstract, and if they do, then it means that they kind of contain similar information, or at least these discriminatory terms captured by the TF-IDF score. Then obviously, like since we're talking here about Wikipedia articles, they all belong to a certain set of categories, and categories try to capture this, let's say, topicality, but of course they are assigned by editors, and in not all cases you have like elaborate category associations, and sometimes these category associations are temporal, basically grouping different articles into different time spans. So what we did first was that we computed representations of these Wikipedia categories. We extracted the Wikipedia anchor graph, and we compute category representation using graph embeddings. And then for each article pair, what we do is we compute the similarity of their categories that they are associated with in terms in this embedding space. And then we do this for the direct categories or the parent categories. And again, since most of the Wikipedia articles have a corresponding entry in one of these knowledge bases, we also check their more, let's say, elaborate or more consistent type taxonomies that exist in knowledge bases like Wikipedia or other knowledge bases, and then see if they are similar. So through this, we try to capture this coarse-grained topical similarity. And obviously, since our main goal is that we want to compute the we want to align tables. So what we want to do is we want to see also like very lightweight set of features that say, okay, so if you have two tables, so the first thing that you should do is if the column headers actually match, and in what positions do they match? Because if I have season in the first position in one table and season in the 10th column in the next table, it obviously means that the tables have completely different semantics, and therefore I should not maybe consider them as a candidate pair. So these are some of the features, and I see that I don't have too much time. So what we do then, we use these features for filtering, and then also train a supervised model to basically classify these pairs as to being relevant or not. And then once we are left with a candidate set, then we go and define like, okay, which actual table pairs can be aligned and which not. So this is a bit more sophisticated. So what we have here, we have since each table has kind of encodes a horizontal and vertical structure. So by that I mean the horizontal is the schema, and the vertical is the table rows. So what we do is that we represent a table through its columns, and each table is a sequence of columns, which we encode here with the gray ones is the column type, which we already have for basically for columns which contain instance values, and for the others, it's basically a non-existing type. And in the case of instance values, again, we kind of average the representation of these instances through some graph representation. And then we have the textual representation, which is just the column header, right? And then we have we encode these tables by using bidirectional LSTM. So what is interesting here is that we have here this delimiter, which is basically initialized by the last column representation of the source table, and then you basically try to generate the representation of the target table which you want to align to. And on top of this, on all these hidden representation, you try to compute the sub alignment between columns in the target table with the source table. That gives you basically with which column one column in your target table is matching to, and you also have this position information. And then the last basically column in the target table, what it will the representation is computed based on this column by column attention, what we call. Then you use that representation for classifying that a pair of table can be a subpart of equivalent or no relation at all. And yeah, the column descriptions, I think I might just skip that because then I might not have time to go into the evaluation. But basically what we use for representation of the tables, we have the column description, which is the column header, the instance values, which are the cell values in a column, and the type of a column in the case of instance value based cell values. So in that case, we just use the least common ancestor type for all these instance values, right? But you can find more information in the paper. So the setup, again, there's no ground truth. This is kind of a novel task. So what we had to do is that since we want to ensure coverage, we cannot go for a very large scale evaluation. We took a random sample of 50 Wikipedia articles. And what we have to do then, we have to ensure that for each of the tables in these 50 articles, we have to ensure coverage so that all the tables from other articles, in this case, 530,000 articles, we can find the relevant ones. We have to do this in an efficient manner. So what we do that you construct manual filters to remove articles which are not relevant. And once we have done this, we do this multiple iterations. And in the last step, then we basically crowdsource the remaining pairs. And since the task is quite complex, you're given two tables, and then you have to decide between subpart of or equivalent. Then we provide comprehensive worker training in the crowdsourcing platform so that they have detailed instruction on how to actually conduct this labeling task. So from all these kind of different steps, we crowdsourced 17,000 table pairs, out of which 52% had no alignment, and the remainder had equivalent and subpart of alignments. And the ground truth is available as well for download and can be used as a benchmark for a similar task. Okay, so for the first step, as I said, we had this feature set which we computed. So we first used them for pre-filtering, then we modify a random forest classifier such that we kind of optimize it to increase the recall, since we want to have high coverage in these table pairs. And then basically here, what you see in this plot, that for the variant classification confidence, so how does it look if you're more confident, how many of the actual relevant table pairs you retain and how many you drop. So for us, like we had a roughly of confidence score of 0.5, where we have a reasonable coverage of 80%. And so then we use this to kind of filter out these candidate pairs, and the remainder we use then for the second step, which is a table alignment. And again here, so what is important, like not to bother too much about these results in the table, but in the bottom rows you have this TableNet model, which is this bidirectional LSTM with column by column attention, that you can basically distinguish with high accuracy between the three different type of relations, or two, in this case, equivalent and subpart of, with roughly an accuracy of 83%. And there are some baselines. For example, Google Fusion had this project, and that is unsupervised, but we kind of modified it so that we can compare it against two. And their F score is quite low. It is understandable because they also they want to find only related tables, so they do not have a crisp definition of equivalent or subpart of relations in their setup. To conclude, so TableNet in itself, it has its methodology on how we conduct this work, but in the end, it is the knowledge graph of these aligned tables, which I think is quite interesting and important to have. As we saw from the motivation, it can answer really complex questions once you have tables aligned with subpart and equivalent relations. And it improves over existing work because we first are the first to define these fine-grained table relations. And we also provide an extensive ground truth, which gives you coverage guarantees, which has not been done before. So the resources for the paper are accessible in the GitHub page. And as I said, a lot of it is already public, but there is some code that needs some polishing and will be published before the web conference in 2019. I hope I was not too quick, and I would be happy to answer if there's any question at all. Thank you.
Thank you so much, Besnik, for this presentation. So let me ask the IRC and YouTube host if we have any questions from the audience.
No questions on YouTube yet.
Okay.
Nothing in IRC now, but let's see.
Okay. Does the room have questions? Not at the moment. Besnik, I do have a question for you.
Yeah.
As you know, we work. So I imagine this work is very much focused because it's a test work on English Wikipedia. As you know, we work with, in general, we tend to work as multilingual as possible. So looking at the type of features you're using in your models, I imagine this work could be extended to other language editions of Wikipedia, but I wanted to hear your thoughts on that.
Yeah, I mean, correctly noted. So I kind of put too much details into the slide so that I could not really elaborate on the individual features. But yes, so all the features are, let's say they are not language dependent. So all these embeddings, graph embeddings and word embeddings can be trained on different languages, and then they can be operationalized into other languages. The only problem that might be there is that you might not have quality guarantees because you would have to generate ground truth for that. So the ground truth is only for the English Wikipedia right now, but I assume that a similar, especially for the more, let's say, popular localized versions of Wikipedia, let's say like German or Spanish, I think this might work comparably similar. So, yeah.
Okay, thank you very much. Do we have any updates from the channels? Leila, I asked your question, sorry.
We have one question from YouTube. Finn Nielsen asks, has the graph embedding model been published?
I'm trying to understand the question. So the graph embeddings are basically embeddings that, so we use existing work. So we use Node2Vec. So basically they're just applied on the Wikipedia anchor graph. So I think you can apply any graph embedding approach, and you probably will get comparable performances. So I'm not sure. So I know that there's like quite some variation on the embeddings that you get from the different graph embedding approaches, but that was not the, let's say, main focus of the paper. The focus why we computed graph embeddings was for the categories, especially, was that the association of the categories kind of, it follows this taxonomy, and also it's done manually. So we wanted to lift this into a different representation space so that we can have, let's say, more reliable comparisons. But the embeddings basically computed using Node2Vec. I did not publish it since it's like quite some gigabytes, but if Finn wants to have the embeddings for the Wikipedia anchor graph, I would be happily to share that with him.
Excellent, thank you.
If I can, I'm going to ask another question. I'm not sure if this is something possible, but do you think you can extend this to align tables outside of Wikipedia as well from other websites?
Yeah. So so the only step which is kind of what would fall off from the current approach would be this category features that we use in the step of candidate generation. So the rest would have no basic it wouldn't have to change much to be applied to web tables, let's say. So that is something that I have in mind, like to kind of extend to and see, because in the web it's harder to give coverage guarantees because it's simply impossible to do that. In the case of Wikipedia, it was more constrained, the problem on giving these coverage guarantees. It was still quite challenging to do that because it required quite some time and efforts from crowdsourcing and myself as well. But yeah, I think it can be easily done. The only thing that Wikipedia has an advantage with respect to, let's say, web tables is that I think the hyperlinking of the let's say the surface forms to actual Wikipedia articles is more consistent. So and this gives you additional information. In the web tables, you would have to do this through an entity linking step that is geared for web tables. So that would be an additional step that you might have to take in order to have this richer column representation. Other than that, I think it wouldn't change anything at all.
Okay, that's very exciting work. Do we have any other questions from the room for Thomas or Besnik, or from the other channels? I don't hear anything. So if there are no further questions for our speakers, I think we can thank them very much for joining us today. It was an amazing set of presentation. Thank you both very much. And I guess we will see you all next month for the April Research Showcase.
Thank you.
Thank you very much. Thank you, Tom.
Thank you.
Thank you all.
Bye.
Bye.
Bye.